Each and every paper printer in the world is possessed by a small demon. This has been a statement of fact. All right, let's talk about a question from section 3.4, problem 11. So we're supposed to describe some subspaces of R3. Are they lines or planes or all of R3? One, is it clear that those are the only options? Line, plane, all of R3? For subspaces?
Couldn't it be a point?
Good. Yeah. It could also be just the point 0. So an additional option would be the 0 vector. My sneaking suspicion is that they did not give me anything, the result for which is the 0 vector. Hot, weird question that I didn't answer in my basis video. Now I feel bad. What is the basis for the 0 vector?
Is it just the 0 vector?
You'd like to think so, right? But the 0 vector can't be linearly independent. The 0 vector has a basis of nothing. That is a relatively strange subtlety. But it matches my concept of dimension, right? How many vectors are there in the basis? There are no vectors in the basis, ergo it is 0 dimensional.
All right, so any basis that is just a point is no, it has no basis, basically. There's nothing.
So yeah, remember that there's only one subspace that's just a point.
Okay.
Just the 0 vector. If it's a point that's any other point, right, then it's not a subspace because it doesn't contain the 0 vector.
Okay.
So there's this little subtlety that the 0 dimensional subspace is always the 0 vector, and it always has an empty basis. It's a little weird. It's just to make it's to make all the things match. But I'm just going to say that by definition, the basis of the 0 vector is the empty vector, is the set of empty vectors. All right, so let's talk through our spanning sets. So I've got these two vectors, and I'm supposed to wonder, what do these span? Right, so for part A, I'm looking at span of this ghost writing crap is really annoying. Oops, that should be a curly brace. What do you notice about these two vectors? I guess what's my, I'm supposed to think about the subspace spanned by these two things, right? What do you notice about these? You notice anything weird? What should I be checking? I want to know how many dimensional, right, the space is. So I'm looking at my span, and I'm thinking, okay, seems like it could be 2-dimensional. Why can't it be 3?
Because there's only 2 vectors.
Good. Yeah, there's only 2 vectors. So, best case, this is a basis for the span, and there's 2 things in it. Maybe not best case, biggest case, I guess. So, I know that I'm going to call this something. I'm going to call this S as the span. I'm going to say, I know right off the bat that the dimension of S is smaller than or equal to 2. I can also make one observation pretty easily, that it's bigger than or equal to 0. I think I can do just one better on that. What did we say about the basis of the 0 vector?
It's not.
There's not one.
Well, there is one, but it doesn't have anything in it. That's a weird distinction, right? Does this set that I'm talking about, does that have something in it? Yeah, it has at least one thing in it. So I feel like I can scratch this and say it's at least one. I also know it's an integer, so I'm left looking at 1 and 2. Now, what's the question I need to decide the answer to? I need to know, are these linearly independent or not? Do you guys see an answer to that here? Are these two vectors linearly independent? Why are you shaking your head at me, chicken?
Oh, I'm just saying they're not, but I already know the answer, which is why I'm trying not to say anything.
Oh, okay. How about anybody except Jacob? Tell me why these two vectors are linearly dependent. You guys are really getting some embarrassing footage of me here. What do you got? We're just going to sit here until one of you guys answers this. Give me a stab in the friggin' dark, hey? Come on, yeet your dignity into the void. Give me something here. What am I looking for linear dependence? I've got two friggin' vectors, right? I just want to know if they're on a line or on a plane. All right, so for linearly independent, I'm looking for an A and a B, right? So I'm considering, is there an A and a B where I could take these two things, add them up, and get 0? Grayson's out. Come on, dude. Give me a stab here.
All right, fine. They're integer multiple of each other.
Good. They're not even just scalar multiples of each other, right? One's the opposite of the other one. Right?
Yeah.
Perfect. So they're linearly dependent. So A is 1, B is -1, does this? Implies that they're linearly. Oops, that's an upside down I. What are you doing, Joe? Linearly dependent, right? All I was looking for was, is there a other than 0, 0 solution to this? There is. Ergo, they must be linearly dependent. What that means is that I can do without one of them. So I can say S is also the span of, and because there's two, I can just pick one. So it's also the span of the single vector 1, 1, -1. That should really probably have curly braces around it, but I'm getting a little lazy with my sets and my sets of one element. Python has taught me to be lazy. Sorry. All right. So if it's the span of one vector, is one vector linearly independent? Yeah, it's got to be, right? There's nothing for it to be dependent on. The only time we'd have one vector that's linearly that makes a linearly dependent set is when that vector is the 0 vector, right? So this implies that the dimension of S is in fact 1, which means that it is a line. Does that follow? Okay, assuming that it does. All right, let's check out B. We're looking for span of the set of 0, 1, 1, 1, 1, 0, and 0, 0, 0. And again, here I'm thinking, okay, so biggest, it's 3. I'm going to call this S with a little hat on it. So I think the dimension of S is smaller than 3. I'm going to look at this and I'm going to see which one of these is obviously linearly dependent. Which one of these?
Zero.
Thank you, Jacob. That one is obviously not needed. Ergo, this is smaller than 2. The remaining 2 vectors are pretty clearly linearly independent. Why are they pretty clearly linearly independent? I'm looking at this 0 here and this 1 here, thinking, if I'm going to add these together and get 0, the coefficient on this one's going to have to be 0. Okay. If I'm going to add these together and get 0, well, this one's not going to be 0 unless its coefficient 0. Ergo, these are linearly independent. So the dimension of my little guy here is 2, which means it is a what?
Plane.
Perfect. This is, in fact, a plane. Okay. Part number C. Now, this is a little wild because now I'm going to try to write down a span, right? But I have a problem because that set has a lot of shit in it. You guys with me on that? So the set is all the vectors in R3 with whole number components. So can you guys list me some of those? Here, I'll list you the first one. 0 is a whole number, so 0, 0 is in here.
I think it needs to be a 3 by 3. Just, you know.
Oh, fair. Good point. There's supposed to be 3 vectors. Right, the vectors in R3 with whole number components. So that's certainly in there. Let's see. How about this one? 3, 2, 1? Or 3, 2, and 1 all whole numbers? Pretty sure they are. How about this one with 1 that has 6 zeros, a 1 with 5 zeros, and a 1 with 4 zeros? I can count. Shut up. How about this vector, which has 10 to the 950 and -1 and 8? Is that a vector in there?
Mm-hmm.
Why not? Which one of these isn't a whole number? I tricked you. It was shitty of me. I shouldn't have done it, but it did. Zach's nodding. It was shitty of me. All right, let me take it back and make it a learning experience. Why is -1 not a whole number? The whole numbers are 0 and the counting numbers, so that's positive.
I did not know that.
Aha. Yeah, clutch fact. In the progression of humanity, we started counting sheep with natural numbers. And then we started doing writing down of how many sheep people had, and that takes whole numbers. The journey between these two number systems was a couple of tens of thousands of human years. Kind of weird. Humans went from keeping tallies for a really long time. Apparently, it took a super long time for anybody to be like, hey, you know what? It'd be really great if I could write down that I don't have any fucking sheep. Like, I used to have sheep. I don't have any sheep. It would be real nice for me to be able to write down that I currently have no sheep. Like I don't know why this took so long. It actually was kind of the breakthrough that made the rest of math possible. Super cool. Took a really embarrassingly long time. Yeah, we should all be saddened, embarrassed to be upstanding apes with this problem.
Didn't negative numbers come closely after whole numbers, though?
Yeah, hilariously, once you start writing down the idea that you don't have any sheep, it's pretty quick to writing down you owe somebody a couple of sheep. Right, and that just really blows everything up, because once you've got this idea that a number can represent a quantity that's not in the world, then you can do shit like, all right, so we've got 7 sheep and there are 8 of us. How many sheep do we each own? And then it's pretty quick to be like, oh, okay, so I just invented fractions. And then just a bit after that, people started getting murdered for believing in irrational numbers. I'm not sure that actually happened, but it's a fun myth to tell regardless. All right, at any rate, specifically included in all my examples of things with whole numbers in them are going to be this guy, and most unsurprisingly, this guy. If I'm considering a spanning set of all of the vectors like this, I don't need them all. How many do I need? Well, I need these 3, and then we're good to go. These 3 make a basis for R3. Is it the standard basis?
No.
Why not?
The last one's got a 17, you dummy.
Yeah, because I have an unhealthy fascination with the number 17. I don't know why. I just let it's kind of a like medium-sized prime that nobody really pays attention to. It's like 23. 23 is a great number. Just I don't know. I like them. All right. So I've got my basis for R3. I know that's in there. It doesn't matter what else is in there. Once I've got a basis in it, I know this span is everything. So I didn't really call this something, but this makes all of R3. You guys with me on that? Bit of weird nomenclature. If you had to call that something, you would tend to call it space. Right? It's either a point, a line, a plane, or space. I don't know. It's weird. All right, let's look at D. So we're considering all the vectors with positive components.
So wait, real quick for
Mhm.
number C. So
Yeah.
that kind of shows that the basis doesn't have to be a subspace, right?
Oh, yeah.
Like it
The
doesn't have to be
basis vectors do not have to be a subspace. The
Okay.
spanning set of the basis vectors is automatically a subspace.
But these can't be a span since it's only the integers.
Yeah, so remember they're asking for describe the subspace spanned by all the vectors with whole number components.
Okay.
So the thing I'm considering is really the span of this set, and I didn't really I didn't get all of them because I can't get all of them because there's 3 times infinitely many of these friggin' things. Right? There's infinitely many choices for the first coordinate, the second coordinate, and the third coordinate. But at the very least, they contain a basis, and so it must be everything. So if I ask that same question for all vectors with positive components, really what I'm asking is, can you make a basis for R3 where all the vectors have positive components? So does this standard basis have that property? So if I think about this standard basis, right?
Couldn't you just do the same thing as before?
I mean, I feel like maybe I could, right? Oops, that's not the second standard basis vector. Do these have all positive components?
Oh, no.
Yeah, it kind of depends on your definition of the word positive. I would say they don't, but that's because I usually assume that the word positive means strictly positive.
Yeah.
Okay, so let's just add that word strictly in here just to. Because if we don't have the word strictly in here, it's not actually interesting, right? Okay, so the standard basis does not have all. Whoa, that's freaky. Sorry, the writing on the thing is tweaking me out today. All right, so the standard basis does not have all positive components. So what I need to come up with is something that is a basis that has all positive components. So let me think about this geometrically a little bit. So I'm just going to look at R2 quick, right? I'm going to smash a dimension out of this thing so I can look at this sucker. So I'm wondering, is there a way for me to avoid those kind of like, these are kind of my standard basis, right? I'm not allowed to use those. So I just need two vectors that are linearly independent in R2 with all positive components. So I'm thinking to myself, like, all right, so I can't go straight along the x-axis. So I'm going to go like along the x-axis generally. So that's like the vector 2, comma 1, right? Now I need another vector that has positive components that's not parallel to that. You guys recognize that that's all I need for linear independence here is that it not be parallel. All right, so what's another vector like this? If I don't want to, like, I just want to go kind of y-ish, right? So how could I, like, move y-ish while having positive components?
1, 2.
Perfect. Nice, Cody. Yeah, take the vector 1, 2 instead. Okay, so quick thing. The angle in between these is not 90 degrees, right? Does that matter? Did I say in my definition of a basis that thou shalt provide vectors that are perpendicular to one another?
I didn't hear that. Nope.
Yeah, I definitely didn't use the word thou. But also all I needed was a linearly independent spanning set, right? So it wasn't that they were perpendicular. That's like a stronger thing. It's super handy, which is why the standard basis has that property, but not all bases have to have that property. So I think I can make a spanning set out of vectors with strictly positive components, and I'm going to do that using basically the same logic. So we're going to scale this up to 3 dimensions. Whoops. Let's scale that one up to 3.5 dimensions, I guess. All right. So first thing first, this guy, I want to be basically x-ish, right? So how do you make an x-ish vector?
2, 1, 1.
Okay. 2, 1, 1. So that's x-ish and has all positive components. Good. All right, how do I make a y-ish vector?
One, two, one.
Perfect. 1, 2, 1. And z-ish, I'm going to do the same thing. I'm going to do 1, 1, 2, right? Now, the thing I have to wrestle with is, are these linearly independent? You guys see that? One way I could do that is I could actually force this calculation. Another way I could do it is I could look at this matrix.
So it's symmetrical.
Which happens to be symmetrical, right? Which is pretty cool. One, because I just made this matrix up. And two, I could, like, all I need to do is do row reduction to it, see how many pivots it's got, right? If it's got 3 pivots, then it's got 3 linearly independent columns. That would be one option. Another thing I could do is I could augment it by 0 and solve. That amounts to the same thing. Another thing I could do is I could take the determinant of this matrix and just check that it's not 0. Do any of those things. I'm just going to say that I punch this into a determinant calculator. I'm going to get not 0. What does that tell you?
They're independent.
Perfect. They're independent. So this is 3 linear independent vectors that are in my kind of set that I was considering spanning. And so the span of these and whatever, right? The and whatever, not adding anything here, is all of our 3. How do I know that and whatever doesn't add anything? If you're spanning a bunch of vectors in 3 space, what the hell are they going to add once you got the whole thing? It's not like you're going to get 4 space out of this. Does that sort of make sense?
Mm-hmm.
Should be noted, I probably was not exceptionally clear about this in my basis thing. You cannot span vectors that you can't add together. So they have to be the same size. It was in there as an implicit, like, okay, so it's the set of all x's, right, that you form out of linear combinations of these. If you can't make linear combinations, then it doesn't make any sense to talk about this. Does that sort of follow? There's a way to talk about kind of adding weird dimensional spaces, kind of like tacking them to each other. But
I think one of the problems in the book actually deals with that, which I was going to ask about.
okay, yeah. So let's get there in the future for right now. Any other questions about this whole thing?
I'm good.